Welcome back, everybody. This is our second video on improper integrals. In this video, we're going to learn the comparison test. So I need to recall a very elementary integration property. Namely, if I have two functions, f of x and g of x, where the g of x is always less than or equal to the f of x, at least on some interval a, b, then the area underneath g of x is going to be less than the area underneath f of x. So if you have a big function which is greater than a small function, so big, small, then the integral of the big function on some interval is going to be greater than the integral of the small function. So the reason why this is going to be so helpful to us when we're trying to decide whether or not an improper integral converges or diverges is because we can actually work out some integrals which we know converge and some that we know diverge. And if I know that something is smaller than an integral that converges, then its integral must be smaller than the integral that's going to converge. And so we know this one will converge. Or if I know that my function is bigger than something that diverges, something that, say, goes to infinity, then I know that the integral of that big function is going to be bigger than the integral, which is going to infinity. And so this must also go to infinity. Okay? So for us to use this, we're going to need one set of functions, at least, that we know exactly what happens. And this is going to be what's called the p-test. So this is going to be a very special case, but very useful one. So the p-test says that if I integrate from, well, it doesn't really matter. I usually think 1, but it could be any a. We'll assume a is greater than 0. If I'm going to integrate from a to infinity, 1 over x to the p, and it's that exponent p that gives the test its name. If I integrate 1 over x to the p from a to the infinity, then, well, we already looked at the case where p is 1 and where p is 2. And when p was 1, the integral diverged. When p was 2, the integral converged. And so it turns out that there's a special thing. If p is less than or equal to 1, then the integral is going, not to converge, the integral is going to diverge. So we saw that when p equaled 1. And when the p is greater than 1, so we saw it, for instance, when p was 2, the integral converges. Now, you can work out exactly what it converges to in that case, but I'm not so interested in what exactly it converges to when I'm using the comparison test. I just need to know that I have something which doesn't get too big. Okay? Fine. So let's see an example of how we're going to use this. Let me take a moment. I'll erase this, and then we'll do our example. All right, let's get to our example. So here what we want to do is look at this integral from 1 to infinity, x cubed over x to the 5th plus 1, and decide whether or not it converges or diverges. I'm not trying to determine what the integral converges to, if it converges, just whether it converges in the first place. So what I want to do is reduce this to the p-test. And the way I'm going to do it is by breaking this up kind of piece by piece. And my suggestion very often is start with the denominator. So let's look at this x to the 5th plus 1. And I'm going to make a little observation that x to the 5th plus 1, no matter what the x value is greater than x to the 5th. Why? Because I've added 1 to it. Fine. I don't have x to the 5th plus 1 here. I have 1 over it. So I'm going to invert these. I'm going to invert, and I get 1 over x to the 5th plus 1, and I get 1 over x to the 5th. And the way inequalities work, when you invert both sides of an inequality, the inequality flips. So this becomes 1 over x to the 5th plus 1 is less than 1 over x to the 5th. Okay? I don't really have 1 over x to the 5th plus 1, though. I have x cubed over x to the 5th plus 1. Okay, fine. I'm going to multiply both of these by x cubed. And since x is always positive, I don't have to worry about the sign flipping. So x cubed over x to the 5th plus 1 is less than x cubed over x to the 5th. Now x cubed over the x to the 5th, since x is not 0 on the interval, I can simplify that. That's equal to 1 over x squared. So I now have the function that I'm trying to integrate, and I have it bounded by 1 over x squared, a very simple function, and it's of this form where p is equal to 2. So I go back and say, okay, wait, hold on. I have something, the function I'm looking for is smaller than something, okay? So if I have something smaller than something big, then the integral of the smaller will be less than the integral of the big. So let's translate that. The integral of the smaller, x cubed over x to the 5th plus 1, well, I need some bounds here, 1 to infinity, dx, is going to be less than the integral, 1 to infinity, 1 over x squared dx. That's the bigger function, 1 over x squared. But this guy, by the p-test, well, let's see, p is 2, 2 is greater than 1, this converges. This big integral converges. But if this converges, then that means that this guy can't blow up to infinity, because it's always smaller than something that's not blowing up to infinity. So that implies that this integral converges. All right, this process of comparing a function and the integral of that function that we don't know, right? We don't know whether it converges or diverges, to a function where we do know whether it converges or diverges is called the comparison test. So we'll do one more example where we see how this works the other way, where something is going to be bigger than something that diverges. See you in a second. Okay, so here's our final example for the comparison test, where we want to integrate from 1 to infinity, 1 over x plus sine squared x. No idea what the antiderivative is, so the best I can do is hope that I can compare this to some other function. Let's make a little observation. This sine squared, right? Well, that's related to sine function, and we know the sine function is always bounded by 0 and 1. And so sine, or rather negative 1 and 1. So rather the sine, let's start over. Take 2. All right, our final example for the video, we're going to try to integrate from 1 to infinity 1 over x plus sine squared x. I have no idea what an elementary antiderivative for this function is, so the best I can hope for is to try to compare it to some easier function. Notice here I have this sine squared. Now the sine function can never be any bigger than 1, and so the sine squared function also has to satisfy that it's bounded by 1. Now, I don't have sine squared though. I have x plus sine squared. So x plus sine squared is going to have to be less than or equal to x plus 1. But I don't have x plus sine squared. I have 1 over x plus sine squared. So I'm going to have to invert these. So I get 1 over x plus sine squared and 1 over x plus 1. And remember, when we invert, we have to reverse our inequalities. So less than or equal to would become greater than or equal to. So now this is my big function. This is my small function. And so the integral of the big function will be bigger than the integral of the small function. So if I integrate from 1 to infinity, 1 over x plus sine squared x, that is going to have to be bigger than when I integrate from 1 to infinity, 1 over x plus 1. Now, this doesn't look exactly like our p-test situation because of this plus 1. But I want you to go through and do a little substitution. Let u equal x plus 1. The bounds are going to change to 2 to infinity instead of 1 to infinity. But you can see it's really just going to look like du over u. And that means we can use the p-test anyway. Having this plus 1 all it's really doing is shifting the function a little bit. It's not going to change the convergence or the divergence. It may change what it adds up to if it did converge, but it won't change whether it converges. Now, so if I ignore this plus 1, what's the power on the x? It's a 1. And the p-test says that when the power on that x is less than or equal to 1, then your integral is going to diverge. So this guy here diverges. Okay, what does that tell us about the integral we want to compute? Well, we know this integral is bigger than something which is blowing up to infinity. So this also must be blowing up to infinity. So we know that our integral that we want to compute actually must diverge. We don't have to worry about finding an elementary antiderivative. There's no answer to be found here. It's really going to blow up to infinity. All right. Comparison test takes a lot of practice, a lot of working through these sort of algebraic formulations, trying to find the right way to bound things. All right. And there are some good tricks, but you're only going to get them through practice. All right. I believe in you, though. Keep at it. You can do this.